Hi everyone, good morning everyone. So I'm Damien Stehlé, I'm the chair of this session. And for the first talk, we'll have Robin Gillen. So I'll give you the floor.
Okay, thanks Damien. Also thank you everyone for joining this early morning session. So today I'm going to talk about a new fully homomorphic encryption scheme that we designed and which we call the generalized BFE scheme. So this presentation is joint work together with Frederik Verkouteren. Okay, to motivate this talk, I would like to make a comparison between two schemes that we already have today. So on the one hand, there is the BFE scheme. In this scheme, we will do computations, typically over some very small finite fields. And then on the other hand, there is a scheme known as CLPX. In this scheme, we will do computations over some quotient ring of the integers modulo some huge p. Another difference is that in the BFE scheme, we can pack multiple of these finite field elements into a ciphertext. And in this presentation, I will visualize this with these kind of hypercube structures. So in this toy example here, we would be able to pack 8 slots. Another difference is that in the BFE scheme, we can do arbitrary computations that can be interpolated over a finite field via the bootstrapping method, and whereas in CLPX, no efficient bootstrapping is known. And then here are some example parameters. So in the BFE scheme, we could work, for example, with a packing size of 1,200 in practice. And in the CLPX scheme, we could use a characteristic that is equal to this 2 to the 14-bit number that you can see here. So note that this p here is really huge in CLPX. Now, for many practical applications, we would actually like something that lies between BFE and CLPX. So in particular, a scheme that can do computations over a finite field of relatively large characteristic, that also has the possibility of packing, and that can be bootstrapped for arbitrary computations. And as you may guess, these research questions are solved by our generalized BFE scheme. Okay, so in this presentation, we will rely on ring learning with errors. So let me introduce a couple of notations for this. So we will be using these cyclotomic polynomials denoted by phi m, and the corresponding fields will be written as k and r. Then we will often consider some non-zero element of our ring, which we call the plaintext modulus. And then all computations will happen over the ring that is defined modulo this plaintext modulus t. So this is this ring RT here. So in summary, you can see this plaintext ring as if it is defined modulo two polynomials. So on the one hand, we have this cyclotomic polynomial, and on the other hand, we have our plaintext modulus t. Then the main technical difference between BFE and CLPX is that BFE instantiates this plaintext modulus as an integer, whereas CLPX uses a linear polynomial. Okay, our generalized BFE scheme, which we also abbreviate to GBFE, is a unification and generalization that covers both schemes. Now I have to say that the encryption and decryption generalize pretty trivially, so they will not be the main focus of this talk. So here we also use ring learning with errors, and in the slides I will denote this with these color diagrams. So I will always write the message in this green region and the noise in this yellow region. And then as usual, decryption works correctly as long as the message and the noise do not overlap. One important functionality that we need in our generalized scheme is a function that chooses small representatives mod t, and for this we introduce this flattening notation here. So when we analyze the output norm of flattening, we see that it depends on two things. So on the one hand, there is this red factor. So this basically depends on the cyclotomic ring that we use. And then there is this blue factor. This blue factor represents the size of the plaintext modulus. So from this inequality, you can already see why we want to use plaintext moduli of small norm, since if this blue factor is smaller, then the output of flattening will also be smaller. And this will be advantageous to our scheme. Okay, to make this a little bit more concrete, I have a couple of examples. So where t is an integer, for example, t is equal to 5 in this first example, then flattening will just correspond to a coefficient-wise reduction mod 5. If t is a linear polynomial, here x minus 4, then flattening will just be a base 4 expansion. So this means that we replace 4 with x everywhere. Finally, flattening can also be defined for a more general polynomial. So in that case, we still see that the output is a polynomial with small coefficients, but there is not really such an interpretation. It's not a coefficient-wise reduction and not a base b expansion. Okay, the next thing to explain is how we can compute unencrypted data. And in this slide, I will do a case study of homomorphically multiplying a ciphertext together with a plaintext. So to do that, the idea is that we're first going to flatten the plaintext. This gives us some m hat, which, as we explained on the previous slide, has small coefficients. And then this m hat will be multiplied by each component of the ciphertext. Then, as usual in FHE, the output noise will be bigger than the input noise. And for correctness of decryption, we should really have an estimate on this output noise. This is given by this inequality on the slide. So here you can see that the output noise depends on the input noise, but also on the flattening bound that we derived on the previous slides. And here from this inequality, again, you can see that using smaller plaintext moduli is advantageous, since the smaller the plaintext modulus, the smaller the norm of our noise growth will be. Okay, so let us now study the plaintext space of our GBFE scheme a little bit more. So here we start from this general identity that always holds for cyclotomic polynomials. And in contrast to the CLPX scheme, we instantiate our scheme with a nonlinear plaintext modulus. So we take it as x to the k minus b. And then since we have that x to the k minus b is in our plaintext ideal, we actually have that x to the k is equal to b in the plaintext string. So in other words, we may substitute x to the k with b everywhere. So this is basically a case of Euclidean division. So if you do that, we can replace this cyclotomic polynomial here by its own evaluation, and x to the k is equal to b. Okay, so our plaintext ideal simplifies to this right-hand shape. So as a result of that, we get native arithmetic modulo this integer that we call p. For the rest of this presentation, we will always assume that p is a prime number, and we will call it a cyclotomic prime because it is obtained by evaluating this cyclotomic polynomial into this integer. Okay, so let me consider a couple of concrete instantiations. So first prime that fits in this cyclotomic shape is this 16-bit prime, which we also call the Fermat prime. Note that this prime is not just achieved for a single plaintext modulus. So there exists a whole family of plaintext moduli parameterized by this I here that give you exactly the same prime p. Now it turns out that each of these parameter sets within this parameter family has different properties, and this is illustrated in the table. So in this table, you can see that the leftmost parameter set, where I is 0, we have a small number of slots, so a small packing size, but also a small multiplication noise. On the right-hand side, which coincides with regular BFE, we have a larger number of slots, so 16,000 slots, but also 2.5 times more multiplication noise. And then anything in between that you would like can also be defined. Another interesting prime, especially for zero-knowledge applications, is this 64-bit prime, which we call the Goldilocks prime, and this also fits in this cyclotomic shape. So for this prime, we could generate a similar table with the same conclusion. Namely, we have this trade-off between slots, where the leftmost parameter sets have a small number of slots and small noise, and the rightmost parameter set has a large number of slots and a large noise growth. Note, however, that in this case, the gain from using our generalized scheme is even bigger, since this leftmost parameter set has 7 times smaller noise than the rightmost one. Okay, now I'd like to dive a little bit deeper into this ciphertext packing and the hypercube structure. And let me start with an example for the regular BFE scheme. So in this example, you can see a 3 by 3 by 4 dimensional hypercube, and you can think of each of these minicubes as if it holds one finite field element. Then one crucial operation that we need in the BFE scheme is permuting these plaintext slots. So in this example, you can see a permutation in the vertical dimension. So this means that each slot will be moved up by one position, and then the top slots move back to the bottom. So for that reason, these permutations are also called circular rotations. Now in the generalized BFE scheme, recall that we have a smaller number of slots, and because of that, only a subset of the slots in this hypercube will still be valid. So those are the slots colored in green on the slide, and the red slots do not contain any useful data. Okay, so in technical terms, what happens here is that the structure of these green slots is determined by the Galois subgroup that fixes the plaintext modules. And somehow you can compare this a little bit to what happens in the regular BFE scheme when we compute over a base field. So in that case, also we have this folding of the Galois group. Now, because of the special structure, we need to be very careful when implementing these rotations that we always map valid green slots to other green slots. You can never map a green slot to a red slot, since the red slots do not contain any data in the first place. One operation that already existed for the regular BFE scheme is ring switching. So in ring switching, the idea is that we will change the cyclotomic ring during the computation. So this, we generalized this operation to our new FHE scheme. Okay, so what happens here on this hypercube is that we're going to process a larger hypercube to a smaller one, and as a side effect of that, also the number of slots in the toy example reduces from 2 valid slots to only 1. Another interesting operation that we have in this generalized scheme is a conversion method. So on this slide, we will be converting a GBFE ciphertext to a regular BFE ciphertext. Note, however, that this only works under constant p. So we can never change the prime p that is used in the scheme. On the hypercube, what happens is that we're going to process this GBFE hypercube, where only 2 slots are valid, to a fully defined BFE hypercube. Okay? And so the red slots here on the left-hand side will simply contain garbage on the right-hand side, and the green slots on the left-hand side will just be copied from left to right. Now note that the conversion routine from previous slide doesn't really use the available BFE space efficiently, since there are many of these garbage slots. And for that reason, we also propose a packing method that assembles multiple GBFE ciphertexts together into one BFE ciphertext. Okay, so what happens here is that this time we get as input multiple GBFE hypercubes. And we're going to convert each of these to regular BFE using the procedure from the previous slides. On top of that, we're also going to put 0 in these red garbage slots. And then finally, we will map each of these slots from the second hypercube 1 position to the left. This is so that they will not interfere with the slots from this first hypercube. And then everything is added and forms one nicely packed BFE hypercube. Now note here that I seem to be mapping a green slot to a red slot, whereas previously I said that this was impossible. But note that actually this mapping comes after we have already converted to BFE representation. So by that point, the mapping is actually allowed. Okay, so we also introduce a bootstrapping operation for our scheme. So bootstrapping is basically the operation where you're gonna reduce the noise of your ciphertext via homomorphic decryption. Now it turns out that due to certain limitations, we were not able to instantiate all of the bootstrapping steps directly in the GBFE scheme. And for that reason, we also crucially rely on this conversion method to regular BFE. So you can see in particular that in this diagram, some of the steps here are evaluated in the BFE domain, but then the final step is evaluated in the GBFE domain. Okay, so we implemented this bootstrapping step in the Microsoft C library. And this table shows you some experimental results that we took. So this is single-threaded and for 128-bit security. Now, a big difference with previous bootstrappings for the regular BFE scheme is that we can instantiate our bootstrapping with much smaller parameters. And in particular, in this slide, we only use the 2 to the 15 cyclotomic ring. And this is enabled because of the smaller noise growth of our scheme. Because of these smaller parameters, we also have much smaller bootstrapping latency. So you can see that the total execution time is only on the order of 2 seconds, whereas BFE bootstrapping for similar parameters typically takes up to 10 seconds. Another interesting line here is this remaining noise capacity. So this basically models the room that you have left for further computation before the next bootstrapping needs to be initiated. Okay, and here you can very clearly see this trade-off between packing and noise. For example, in this left column, with a small number of slots, we have a large remaining capacity. But in this rightmost column, with a large number of slots, we have a small remaining capacity. And this is basically because the bootstrapping itself has more noise blowup in the rightmost column. Okay, so to conclude, in this presentation, I explained our method of more efficiently instantiating these large cycloatomic prime fields in FHE. Our method has this very flexible trade-off between packing and noise, which allows us to bootstrap in lower latency. We were unable to instantiate all of the bootstrapping steps directly in the generalized BFE scheme. Therefore, we also rely on this conversion to regular BFE. So bootstrapping in the generalized BFE scheme in a native manner still remains an open problem. Okay, so I would like to end with this blog post. So behind this QR code, you can find a blog post that I wrote about this paper. So if you're interested in it and you would like a somewhat more lightweight reference than the paper itself, then I recommend reading the blog post. And with this, I would like to thank you for listening.
Thank you for the nice talk. Are there questions in the audience? Okay, so I have a quick one. So the types of techniques that you described, does it also adapt to BGV and CKKS? And do you see ways to make them work to this kind of other FHE schemes?
For BGV, I think yes, but we haven't really written it out. But I think it should carry over to BGV in a trivial manner, roughly. For CKKS, I don't think so. You get stuck if you try to do the same derivations for CKKS. It doesn't really work because the encoding of the data is different and the data lives in a different space. It's approximate instead of these finite field computations. So for CKKS, I don't think it will work.
I've got another one. So you get nice compromises between trade-offs between modulus consumption and number of slots. For which kind of applications do you think this is most relevant or most beneficial?
Yeah, it works best for applications in which you have low packing, because in the scheme we can really reduce the latency, but it's not really an asymptotic improvement in throughput. So for that reason, in applications where you have a limited number of packing, for example, only 1,000 slots instead of maybe 30,000 as you have available in regular BFE, so mostly for these applications with lower packing. Yeah.
Okay, thank you. Are there any questions? Okay, so if not, we can thank the speaker again. So the next speaker of the session is Rachel Player. So I give you the floor.
Thank you, Damien. Hi, everyone. Okay, so hi, my name's Rachel. I'm excited to be here today. I'm speaking on behalf of all the authors, so Hiroki Okada, Simon Pohman, and Christian Weiner, and especially Simon, who really led this work. So I'm going to speak to you today about algebraic homomorphic encryption and its applications to doubly efficient peer or d-peer. Okay, so just quickly give some background. So obviously we're in the homomorphic encryption session, so I don't need to go into too much detail about what homomorphic encryption is. I hope everyone's already aware of that. But what we would need to remember for this talk is that it's a primitive that's enabling a client to outsource the computation of some function f on their data x to a server, perhaps a more powerful server, in such a way as their data remains private. So the client encrypts their data x, the server homomorphically evaluates the function f on the encryption of X, and the output is the encryption of f of X, which the client can then decrypt and find the result. And one other thing to recall is that typically the homomorphic evaluation function is actually, if f is not already a polynomial, approximating f as a polynomial. Okay. So we're also interested in this work in private information retrieval. So what is this? So this is a protocol, again, between a client and a server. The server has a database of n entries, and the client would like to retrieve the ith entry of the database. So they engage in this protocol, and at the end, the client hopefully receives this ith entry of the database. But for security, we require that this is a private information retrieval, so the server doesn't learn which index was queried by the client. And to exclude trivial solutions, we need that the communication cost is less than transmitting the whole database over to the client, which would work, but is somewhat trivial. And PIR can be achieved in several ways, but one of the ways it can be achieved is by homomorphic encryption. If you think that you would take the private data X to be the index, and then you evaluate a polynomial that somehow encodes the function retrieving the ith index from that database. So we're going to denote that as P sub dB in this talk. Okay, so doubly efficient PIR, or dPIR. So we saw on the last slide, we need the communication cost to be sublinear in n, but what about the computational cost? Well, there's a few answers, depending on whether you allow pre-processing or not. So if not, then it's kind of inherent that you have to have computational cost at least the size of the database. Otherwise, it would basically imply that the server, if by not processing on a particular entry, the server would learn that that entry wasn't to do with what the client was querying. But if we do allow some pre-processing, then we can make some progress. So there's two flavors. So either you would have a pre-processing that's client-dependent. So every time a client would want to make a query, they have to do a pre-processing step. The pre-processing step is expensive, costing tilde O of n per client, but then the online cost could be less than n. But still, like pre-processing per client could be expensive, and one might want to avoid that. So there's also a setting where a client-independent one-time pre-processing is considered. Again, the state of the art, as far as I know, is still tilde O of n in cost, but after this one-time pre-processing, then many clients can query. And this is the setting where dPIR is living, and specifically dPIR, doubly efficient PIR, is any scheme in the client-independent setting where the online cost is sublinear in n. So it's doubly efficient in the sense that the communication and online cost is sublinear in n. So it was recently shown by Lin, Mook, and Wicks how to construct dPIR, and I'll briefly recall how this construction looks like because we're building upon this. So their result relies on this result of Kedlaya and Oomans from 2011. And it basically states that a multivariate polynomial can be evaluated efficiently if we have a particular pre-computed data structure. So this fits nicely into the dPIR setting where we can compute the data structure in the pre-processing and then efficiently evaluate the polynomial. So in LMW23, what they do is use this polynomial evaluation result homomorphically to efficiently evaluate f sub dB. So there is a slight snag. So while the f sub dB is itself a polynomial, in typical homomorphic encryption schemes, eval of a polynomial may not be exactly a polynomial itself because we have all these ciphertext maintenance operations which we do for efficiency, like modulus switching or relinearization. So we actually need algebraic, somewhat homomorphic encryption, which is any scheme where evaluation of a polynomial on some input ciphertext is the evaluation of that polynomial on the input ciphertext. So we do have these. What's quite interesting is that some of the more modern schemes that we're used to using in HE now are derived from these algebraic schemes as we previously had, but here in this application we really need the algebraic structure. So yeah, we're essentially demanding that the ciphertext space is a ring. Okay, so I can now explain some of our contributions in this work. Okay, so we're kind of motivated to try to improve deep here. So while it's asymptotically very nice, it's practically fairly inefficient. It's still inefficient as a result of this work also, but we tried to make progress towards understanding and improving its efficiency. So one thing we were considering is how much is the algebraic somewhat homomorphic encryption, or ASCII, itself the bottleneck. So our first main result is to show that if we have any post-quantum ASCII scheme that can evaluate polynomials of degree d, then its ciphertext ring size must be at least 2 to the d. So we can see this as somehow like a lower bound on the performance of post-quantum ASCII, so some kind of understanding about how performant ASCII can be. And we can ask, how does this bound compare to the ASCII schemes that we have? So in LMW23, they're using the BV ASCII scheme. There, the ciphertext ring is O to the, it should be 2D, 2 to the 2D. So yeah, bigger than the lower bound. And then if we would compare to something like BGV, BFE, maybe something that we're more used to, this is not ASCII, and the ciphertext space is obviously much smaller. So a question that also still remains open from our work is, can we build ASCII that meets this lower bound? So we weren't able to solve that. So instead, we modified BV to enable more performant DPIR. So I'll explain our modifications, but first by recalling the structure of BV at the high level. So here are 2 fresh ciphertexts in BV. They're degree 1 polynomials in some indeterminate t. The coefficients of those polynomials are elements in R mod Q. Q is some really large modulus. R you can think of as a power of 2 cyclotomic ring. And if we would multiply these 2 fresh ciphertexts, then we get a degree 2 polynomial, and so on. If we would multiply more, we'd get higher degree polynomials. So when you're working with BV, you're working with these large, clunky things in RQ adjoined T. So maybe we can try to work with something more convenient. So we can first appeal to an idea which we use often in HE, using a double Chinese remainder theorem representation. That's going to enable us to work on polynomials whose coefficients are in F mod P for some P dividing Q, instead of the whole big RQ. So that gives us something. And then our next, maybe more main idea, is to change how we express the evaluation of F on M input ciphertexts. So we would rewrite that as a sum over the powers of T of different polynomials F sub I, where now the polynomials are just over Fp. Okay, so that's the expression from the previous slide, and we are going to go one step further. So we have 2 M variables now over Fp, and we're going to fix M of them to be binary. So this then means that for every possible choice of the BI, we pre-compute the Fi adjoin the BI. So we're only processing on M variables in the end. And why do we want to do this? Well, if we would increase to 2M, then we're actually increasing the storage cost, which is not very desirable. But by fixing the BIs and doing the pre-computation for every fixed choice of BI, we can collapse back to having M variables again. So what does this correspond to on the underlying BV? So again, here's a fresh ciphertext. And what's underlying the in CPA security of BV is that the components of the ciphertext are forming a ring LWE sample. So by fixing the BI to be binary, we're modifying the underlying ring LWE assumption. So now we have one where the B part of the ring LWE sample is such that if you would map it into the CRT space, its components would all be 0 or 1. Okay, so we're introducing this new problem. We're calling it 0, 1 CRT ring LWE. And of course, we analyze the problem to have some confidence in using it. So I'll quickly define the problem and then show our next main result. So we're working with the 0, 1 CRT set. So we can call this set S. This is a set of elements in R mod Q, such that you can obtain it by taking the, in the CRT space, the set of elements there that have only binary components, then map them back under the CRT isomorphism inverse, and then you'll recover a set in RQ. So then a decisional 0-1 CRT ring LWE is the following problem. You take your B from this set S, the 0-1 CRT set, then we take off an error, then we multiply by S inverse, where S is some fixed secret, and we call that output A. And then if I have pairs AI, BI formed this way, the problem has to distinguish such AI, BI from uniform entries. So it looks similar to ring LWE, except we're using the 0-1 CRT set for the B. And we actually show that assuming some technical conditions on the modulus Q, if standard ring LWE with preprocessing is hard, then 0-1 CRT ring LWE with preprocessing is also hard. So this gives us some confidence in this assumption. And in the preprocessing phase, so before the ring LWE oracle is queried, the adversary has access just to R and Q. So that's what the preprocessing allows. Okay. We also implement our improved DPIR based on these modifications, and I'll just tell you the headline results. So we do get a reduction in read queries. It's 8 times for parameters we can actually run, and we can estimate that it would be 23 times for larger parameters. Yeah, DPIR is still inefficient, so it can't really be run for the larger parameters yet. But where we can run, we get a speed up of more than 4 times as well. So zooming in on the read queries, I've got a graph here that's plotting database size against the total read queries, and we're comparing with our prior work, which is the only other implementation of DPIR, as far as I'm aware. So the dotted line is our prior work, and the solid lines are the new work, and then there's different colors for different choices of M. And so what we basically see is we're kind of getting one variable for free. So the old M equals 5 line is now the M equals 4 line, and same for M equals 5 and 6. And yeah, so for any kind of fixed database size, you can see that, and for any choice of the M we've considered, the new approach has fewer read queries than the prior approach. A similar looking graph, but this time we're also comparing the storage. So here, again, we have the same dotted line for prior work and solid line for this work. And yeah, we've got database size against data structure size, and we see that the storage size stays about the same as prior work, while we've had that read query improvement. Okay, so I have some time to conclude. Okay, so let me summarize again what we've contributed in this work. So we first conducted a theoretical study of ASHI, and we've given a lower bound on the performance of any post-quantum ASHI. We also looked at ways to improve DPIR, so we presented a modified BB scheme, which is based on 0-1 CRT ring LWE. I didn't have time to explain it today, but we also show in the paper an additional improvement to the polynomial evaluation data structure. We implement these improvements and compare the performance to our prior implementation. And then we study the hardness of 0-1 CRT ring LWE, and we give a reduction that goes from standard ring LWE to actually a wider class of reduced entropy variants of ring LWE, of which 0-1 CRT ring LWE is one example. So yeah, see the paper for details if you're interested in that. And we also consider a preliminary cryptanalysis. I think more work would be needed here, but we kind of look at the concrete algorithms for LWE and how we might adapt them to see if there's any improvement for 0-1 CRT ring LWE. And we initially found, apart from maybe a slight tweak to BKW, yeah, nothing too alarming at first sight, but I think more work should be done. Okay. So our work also leaves many open questions. So yeah, one of the kind of motivating questions of our work we weren't actually able to answer. So does there exist a post-quantum ASHI scheme whose performance in the sense of ciphertext ring size meets the lower bound we have? Then we can think of other ways we could potentially improve DPIR. So one can think of this modified BV as a kind of relaxation of ASHI, so it's no longer an ASHI, but it is sufficient to construct DPIR. So maybe there's other ways of relaxing ASHI to construct DPIR. Or maybe there's other approaches more generally to making DPIR more efficient or constructing it generally. I really think more should be concretely studied on 0-1 CRT ring LWE. or the other reduced entropy variants we're interested in. And yeah, so we have this new class of ring LWE problems. Perhaps they're useful to making other applications more efficient. So yeah, I'd be interested to see if anyone has any ideas about that. Okay, so our paper, the full version is on ePrint, and our implementation is also available on GitHub. Thank you very much.
Thank you, Rachel, for the presentation. I see that there are questions. So
Yeah, so really cool talk.
Thank you.
I'm getting old, so my memory's not so good. So in your graph, you talked about this value M, and you said improved
yeah.
M. I couldn't remember what M was. What's M?
Oh, it's so we've got like 2M variables, so it's like how many BIs are fixing.
Oh, I see. Oh, okay. Yeah.
Yeah, thanks.
Hi, this is a nice talk. Thank you. I just, I'm not very familiar with this double CRT method in the FHE literature. Like, can you expand more about how that kind of interacts with the usage of CRT in like the KU preprocessing? Like, is there any interaction there, or like?
Maybe it's better to take the question offline.
Okay, yeah, sure. Yeah.
I don't know if I can give a succinct answer. Thanks.
If there's time. Can you say a couple words about how the parameters are affected in the 0-1 double CRT? Like, is there any loss in any of the parameters in your reduction?
Not off the top of my head, but yeah.
any other questions? Can you tell us more about the pre-processing?
Might be a little slow here, but I still didn't quite get what M is in the evaluation.
Oh yeah, I don't know if I can't get the slide back up, but so we have, if we're processing on M ciphertext, then we have like 2M variables in the multivariate polynomial that we're evaluating over, like the F sub I, and then B1 to Bm, so it's that choice of M.
But is that an internal parameter or like PIR problem statement?
The internal.
Thanks.
Any other question? Okay, so let's thank the speaker again. Okay, so the last speaker of the session is Alexandra Henzinger. And Alexandra, the floor is yours.
Perfect. Yeah, thank you. So hi, I'm Alexandra, and I'm going to talk to you today about building homomorphic encryption from new assumptions. And this is joint work with Henry, Yale, and Vinod. Okay, so an encryption scheme is homomorphic if it lets anyone perform computations directly on encrypted data. So in the setting, we have a user that can sample a secret key and an evaluation key. And now our user can publish its evaluation key and then can publish encryptions under its secret key of any messages x1 through xm. And now what we want is for any party that has received these values to be able to evaluate directly on these ciphertexts. So here our server can take any function in the supported class and should be able to produce the encryption of the function f applied to x1 through xm without ever decrypting and without learning anything about the underlying encrypted data. So to be a little bit more formal, we require such a scheme to satisfy 3 properties. So first of all, it should be correct, which really just means that the ciphertext produced by the server here really does decrypt to the function f applied to x1 through xm. Second, our scheme needs to be semantically secure, which means that the ciphertexts, together with the evaluation key, should reveal nothing about the underlying encrypted values. And finally, our scheme needs to be compact, which means that the bit length of all of the ciphertexts here should not grow with the complexity of the function f that we're evaluating on this encrypted data. And really, the intuition for this compactness requirement here is that you can think of this protocol as outsourcing the evaluation of f to the server. So really, it had better be that the communication here is smaller than in the trivial construction where the server would just send f to the user. Okay, oh, and so the reason why we care about homomorphic encryption is because we know that it gives us a whole range of privacy-preserving applications. So for example, you could imagine F here being a machine learning model or being some secure genome analysis functionality. And so with homomorphic encryption, we can evaluate these directly on encrypted values. Okay, so as the definition of homomorphic encryption implies, this primitive really exists along a spectrum depending on the complexity of the functions that you can evaluate on encrypted data. So at the bottom here, we have private key encryption, which is not homomorphic. Then above this, we have linearly homomorphic encryption, which can only evaluate linear functions, so only additions on ciphertexts. And then at the top here, most powerful, we have fully homomorphic encryption, which can evaluate any function on encrypted data. So really, the way to think about this for this talk is it can evaluate any number of addition and multiplication gates on encrypted data. And so in between linearly and fully homomorphic encryption here, there's a huge range, and we refer to these as somewhat homomorphic schemes, which sort of get more powerful as they're able to evaluate more and more multiplication gates. Okay, so what do we have? Well, one-way functions give us private key encryption, and a whole suite of number theoretic assumptions give us linearly homomorphic encryption. What's more, it turns out these schemes can also be boosted to compute some nonlinear functions, so to compute certain branching programs on encrypted data. Then in 2005, we learned that using cryptographic pairings, we can evaluate degree 2 polynomials. So this is one multiplication and many additions on encrypted data. And in 2009, we learned that using lattices, we can get all the way to FHE, and also that we can get there using the machinery of I/O. But really, this is it in terms of the approaches we have to homomorphic encryption. And in particular, if we want to homomorphically evaluate polynomials of degree 2 or higher, really lattices and then pairings are all that we have. And so this talk is going to be about a new approach to building homomorphic encryption. And what we're going to do is we're going to build a somewhat homomorphic scheme that's going to let us perform a few multiplications and then many additions on encrypted data. And so the way we're going to get there is by combining two tools. So first, we're going to take a linearly homomorphic encryption scheme, which is this balloon here given to us by number theoretic crypto. And then we're going to see how to lift this linearly homomorphic scheme into a somewhat homomorphic one by adding in just one extra assumption. And this is an assumption that on its own has no homomorphism. So on its own, it just gives us private key encryption. But what we see is that when we put these two things together, we get something that's much more powerful than either individual part. And so that's what this talk is about. So we're going to see how to combine the sparse learning parity with noise assumption, which is this assumption that on its own only gives us private key cryptography. And we're going to put it together with a linearly homomorphic encryption scheme and then get a somewhat homomorphic encryption scheme. And this scheme is going to be such that for any parameter n that is polynomial in our security parameter and that we sort of commit to at encryption time, we're going to be able to perform just slightly less than log n multiplications followed by n additions on encrypted data. Okay, and so let's begin by talking about this sparse LPN assumption. So this assumption was introduced by Alec Novich in 2003, and it's based on the following problem. So say I sample a random matrix A of dimensions n by n, which is sparse. So every row in A is going to have exactly k non-zero entries for some parameter k that you should just think of as super constant. And then I'm also going to sample a secret vector S, which is truly random and of dimension n. And what I'm going to do is I'm going to publish A, and I'm going to publish A times S corrupted with some noise. And specifically, this noise is going to be such that almost all entries are 0, but with some tiny, so inverse polynomial in n probability, so say n to the minus 0.1, the entries in E here are going to be truly random values in the field. So now, okay, I'll publish A times S plus E, and I'm going to ask, can you distinguish this from just a random sparse A and a truly random vector B? And it turns out, to the best of our knowledge, the answer here is no. So this is closely related to the hardness of random constraint satisfaction problems and other problems in average case complexity. And just to give you a sense of what this means for crypto, so in higher noise settings, we know that sparse LPN is implied by the standard LPN assumption. And in this setting that I've given you here, we know that sparse LPN gives us a handful of cryptographic primitives. And among them, we have PRGs and NC0, and also a very cool construction of homomorphic secret sharing that inspired this work. Okay, and we're going to use sparse LPN now to build homomorphic encryption. And the way we're going to do this is really in 2 steps. So in a first step, we're going to use the sparse LPN assumption to give us a scheme where we can homomorphically add and multiply. But this scheme is going to have one major catch, which is that the ciphertexts are going to be enormous. So in fact, this scheme is not at all going to be compact. But these ciphertexts have the appealing property that decrypting them is very, very simple. So it only requires evaluating a linear function in the secret key. And so then, in a second step, we're going to use a linearly homomorphic encryption scheme to shrink down these ciphertexts and make them compact. And so now I'll step through each of these 2 ideas in much more detail. Okay, so at a very high level, our goal is going to be to build an encryption scheme that looks as follows. So what we would like is for our ciphertexts to just be square matrices, and for our server to, whenever it wants to perform a homomorphic addition gate, to just have to add the matrices. And whenever our server wants to perform a homomorphic multiplication gate, it should just have to multiply the matrices. So really, for those of you who are familiar, this should look very close to the Gentry-Sahai-Waters fully homomorphic encryption scheme from lattices, but here we're trying to port it to code-based crypto and to using this sparse LPN assumption. And one more property that we want is we want this decryption function to be linear. Okay, so how should we do this? Well, again, following in the footsteps of Gentry, Sahai, and Waters, we're going to have our ciphertexts have some special structure. So we're going to have our user sample its secret key to be just a random vector S of dimension n. And then to encrypt any message X, what we're going to do is we're going to build a sparse matrix C into which we've embedded X as a noisy eigenvalue. So just to be very specific about what I mean here is we need this key equation here to hold. And this equation says that if I take C and if I multiply it by minus S1, so you can just think of this as sort of the extended secret key vector, then what I should get back is X multiplied by minus S1. So this here really means that X is an eigenvalue, minus S1 is an eigenvector, plus some sparse errors. So I'm okay with this equation only holding in most positions. Okay, so the first thing you might ask is, how can we build a ciphertext of this special structure? And we're going to do this as follows. So to encrypt, we're going to sample a sparse A matrix, and we're going to publish this up with one more column appended to it. And we're going to compute this column as A times S, plus our sparse LPN errors E, plus our message X, multiplied by this extended secret key vector. So if you stare at this for a bit, you see that this does indeed meet this key equation. And what's more, it turns out we can prove that this computationally hides the message X using sparse LPN. Okay, so now I've argued that we can build ciphertext of this form. And it turns out that this special structure here is incredibly useful for performing homomorphic operations. So specifically, if we add 2 matrices, the underlying eigenvalues add, and so we get an encryption of the sum of the underlying messages. And in the same way, if we multiply 2 ciphertexts, the underlying eigenvalues multiply, and we get an encryption of the product of the underlying messages. And finally, our decryption is indeed linear, because to decrypt, we just need to take our ciphertext, multiply by minus S1, and then the last entry there is going to be exactly X, plus some error term with very low probability. Okay, so this really is it. So we just built a scheme that's correct, it's secure, and it's homomorphic. And if we step through the error analysis here, we see that if our secret key is of dimension n, then this scheme here can support just slightly less than log n multiplications, followed by some polynomial in n number of additions. So really, this is nice because n is just a parameter of the scheme, right? We can make n as big as we would like to support however many operations we need. But unfortunately, what I just said should be a huge red flag, because n here is also the dimension of our ciphertexts. So what I said really is that to compute more of these ciphertexts, we need to make them bigger and bigger. So what we get is a scheme that's not at all compact. In fact, it turns out the bit length of these ciphertexts is always bigger than the bit length of just representing the function f. So the server would be way better off just sending f to the user instead of computing on and sending around these big, bulky ciphertexts. Okay, so this is bad, but the good news is that we've only used one of our two ingredients, and so we're going to try and save this by adding in linearly homomorphic encryption. And the way we're going to do this is as follows. So right now, we have a procedure for our server to get as input a large sparse LPN ciphertext, to compute on it, to produce an encryption of the output. And really what we would like is to give the server a mechanism to just shrink down this ciphertext. So we would be really happy if our server could take this large sparse LPN ciphertext and translate it to a compact ciphertext, say from a linearly homomorphic encryption scheme that encrypts the same value. And it turns out we can do this just with the observation that decrypting our sparse LPN ciphertext is a linear function in the secret key. So really, all we need to do here is we need to publish a linearly homomorphic encryption of our sparse LPN secret key. And now any party can homomorphically run this decryption function, and what it's going to get out is going to be exactly a linearly homomorphic encryption of the same output message, so of f of x here. Okay, so this is good, right? We've partially solved our problem. Our server can now squish down its output ciphertexts, but still, you might argue that our input ciphertexts here are large. And the good news is that we can solve this with essentially the same trick again. So what we're going to do is instead of having our user upload the large sparse LPN ciphertext encrypting x, we'll upload a ciphertext encrypting x from an encryption scheme that's compact and that has a cheap decryption function. So we can also build this from sparse LPN. I'll just call this the orange scheme for now. And so then what we see is that as long as the orange scheme's decryption function falls within the circuit class that our sparse LPN scheme can compute, we're good. And so what we can do is we can just publish our somewhat homomorphic encryption of the orange scheme secret key. And now anyone can homomorphically decrypt this orange ciphertext to exactly obtain our large sparse LPN encryption of the same message. Okay, so putting this all together, we get a final construction that looks as follows. So again, we have our three schemes. The first one has cheap decryption, the second one is homomorphic but not compact, and the third one is linearly homomorphic. And what our user needs to do is it needs to sample a secret key for each scheme, and then it needs to publish a one-time evaluation key that really is just going to be a chain of encryptions of one scheme's secret key under the next. So this is exactly the material that we'll need to perform these translations. And so now what our user can do is it can encrypt its values using just the compact orange scheme. Our server can sort of locally in its head translate these to our sparse LPN ciphertexts, then perform whatever computation it needs, and then squish this back down to a linearly homomorphic ciphertext. And so what we get is that all of the ciphertexts that are sort of communicated on the wire between the user and the server here are compact. And all of the blowup from working with sparse LPN is constrained to the evaluation key and then the local computation on the server. Okay, so this really is it. This is the entire somewhat homomorphic encryption scheme. So what we saw in this talk is that we can combine the sparse LPN assumption with a linearly homomorphic encryption scheme to get something much more powerful. And so we performed a few multiplications and many additions on encrypted data. And so I just wanted to leave you with some open questions. So the first question here is whether we can improve the efficiency of our schemes, both in theory and in practice. The second question is whether we can hope to get homomorphism from even less. So here really we tried to get down to these two relatively lightweight assumptions, but can you do it from fewer assumptions or maybe from even weaker ones? And finally, maybe in sort of the moonshot question here is whether we can fly even higher. So whether there's some way to draw more homomorphism from these schemes and to get all the way to fully homomorphic encryption. Yeah, so thank you so much.
Thank you, Alexandra. I see that Nigel has a question.
Yeah, another cool talk. Have you thought about whether you can verify the computation? Because it's just additions and multiplications of matrices, so it looks like you should be able to get really efficient, verifiable SHE.
That's a very good question. The answer is no, we didn't think about it. So I totally, I buy your intuition that this seems amenable to this sort of thing. Yeah, it would be very nice. Yeah, it would be very nice.
Yeah, very nice talk. But are you saying you believe sparse LPN is a weaker assumption than LWE ring LWE, or why is that?
All I'm saying is that we know less from sparse LPN. So LWE gives us fully homomorphic encryption and whatnot. And in the parameter regime we've used it here, and we don't even know whether sparse LPN gives us public key encryption. So in that sense, it would be a big result to show that it does.
Thanks. And since one of your motivation is this privacy preserving primitives, have you tried using it on PIR, and how does it compare to existing ones?
Yeah, it's a good question. So we haven't gotten to implementing this yet. So this would require sort of estimating the parameters of the scheme. I think the major bottleneck in terms of efficiency is going to be this evaluation key, which for us is large. So finding a way to shrink down this evaluation key would be extremely cool. But if there was a way to do that, I think there are some properties here that are appealing. So one of them is that LPN works over these very small moduli. So you could even imagine working over F2, whereas with LWE, you usually have to work over much smaller things. So this, for example, could be interesting for some applications.
Thank you. Any other question? Okay, so I propose that we thank the speaker again, as well as all the speakers of the session.